Today we will have two talks by our colleague Jobst Landgrebe. Jobst, born in 1970, studied philosophy, medicine, biochemistry, and mathematics. After he obtained his MD PhD in 1998, he worked as a biochemist and biomathematician for 8 years at the Max Planck Institute for Psychiatry and Neurogenetics and the DFG Center for Cell Biology. He then switched to the private sector in 2006, where he has worked in various research and development positions, always with focus on AI, and mostly for the pharmaceutical industry. He regularly publishes in the fields of theory of science and political philosophy. He teaches theory of science as guest professor at the universities of Buffalo and Lugano. As you probably know, Jobst published recently a book in Routledge co-authored with the philosopher Barry Smith, in which they argued that machines will never rule the world. And in this first talk, Jobst will explain the core argument of this book. So thank you very much for coming, Jobst. A great pleasure. And
thanks a lot for the invitation. I feel very honored to talk to you today about our book and also some of the more recent developments in AI that we, of course, have all predicted in the book. This book is about the essential limits of AI, and the essential is now outdated. We have in philosophy two main branches that now dominate. One is analytical philosophy, and the other one is Heideggerian anti-rationalism. So, to which we get back this afternoon. But within analytical philosophy, there is a very strong Humeanism that is fashionable, so that the essential properties are almost thought not to exist. But I think that they exist, and they give us, and also physicists believe this, and they give us the arguments that we need for today. So AI is extremely fashionable. You see there have been 3 waves of AI since the 1950s. The first one was from 1950 to 1975, where they created logic systems and stochastic models. You can see one there, the ELIZA chatbot, which Weizenbaum developed in the 60s to show the limitations of computers. Then the expert systems, which were from 1980s to 1990s. Here you have, as an example, the IBM machine that beat Kasparov in chess in 1996. I remember it. I was very impressed, because at the time I hadn't studied mathematics yet and I didn't understand how it worked. Now that I understand how it works, I'm a bit less impressed, very much less impressed, but then I was impressed. And basically remembering that time, and myself, how naive I was at that time, I can understand why now so many people believe that the new third wave of AI is now the real AI, which it is not. And now today we have stochastic learning with deep neural networks. Stochastic learning has been invented by Gauss and Legendre already around 1800, but it was only made computable in the 70s, and then it became, thanks to the huge computation power that was then created, became feasible only from 2010 on. Also because the internet provides so many data, and you can see here some impressive applications. One is Google Translate, which is used a lot. I use it also every day. Not Google, but another version, which is better than Google. Then there's AlphaGo, which beat a human Go player, which I found very impressive, and the technology behind it is extremely elaborate and can be compared to the Cologne Cathedral in terms of its mathematical beauty. And then we have ChatGPT, which is a so-called foundational language model that is also now very fashionable, and it has created a lot of buzz. And what is this buzz about? Let's look at the AI hysteria that we now have. So I give you 2 examples of quite famous people. The first is Elon Musk, who said last year that he's a climate hysteria entrepreneur and profiteer. It is how I characterize him. But he also is an AI hysteria guy. And he said, soon we won't have to work anymore. The machines will do everything. He really said this. And this is absolute nonsense. And there's also no danger in machine domination. What Musk does here, he knows it. But he has a semi-monopoly on AI. And he wants to protect this monopoly by getting very strong regulation. Because if there's a lot of regulation, new market participants cannot enter the market. That's the only reason he says it, right? It's just to block the market for new entrants. It had nothing to do with reality. But even worse is Geoffrey Hinton, because he has no personal interest in blocking any market. And he really believes what he says. He's a psychologist and computer scientist from the second wave of AI of the 70s and 80s. And he was also at Google Brain. He believes that AI will soon surpass the information capacity of the human brain. Though information capacity has nothing to do with intelligence, I think it surpasses information capacity already since a long time. But that has nothing to do with intelligence. But he says that chatbots would soon have the ability to learn independently and share knowledge, that they can form a collective, which of course is philosophically nonsensical because a collective needs intentionality, which computers don't have, but that taken aside. Then he also thinks that the AI will take over power, and he believes it's not inconceivable that AI could wipe out humanity. He believes that generally intelligent AI systems could create their own goals and that do not coincide with the interests of their programmers. That AI systems would become power hungry and or prevent them from being switched off, like HAL 2000 in the Space Odyssey. And AI systems would become power hungry. And all this is pure nonsense, but he has a point when he says that AI weapon systems are very dangerous, and we will talk a bit about AI weapon systems this afternoon, but not this morning. But this shows you, these people get a lot of attention in the public sphere, and usually people believe this because they believe in success. And Musk is very successful, so they believe he must be right. And so it's a bit like the political philosophy of Napoleon. It was very fashionable. Napoleon was so successful at the beginning of the 19th century that everybody believed his political philosophy was right, but it certainly wasn't, because after him, well, he had some followers like Mussolini and Hitler, but these are not the right people that we want to have as rulers. So it's an example of that success doesn't guarantee that you're right. So let's start with Cartesian sciences. These are the sciences that are used to build this mobile phone, this computer, the camera that we have here. I mean, the architecture of this building, that we have electricity here and this formidable technology. This is all done with Cartesian sciences. What are Cartesian sciences? So they have models of reality. These are representations of an aspect of reality which use abstract symbols. They're used to describe reality, explain it, or even predict aspects of reality. A good example of prediction you can see on the right-hand side is these trajectories in ballistics. Right? These are parabolas of ballistic missiles, and this was one of the first applications of Newtonian and also Leibnizian calculus, which was used to destroy. The German engineer used it to destroy in Athens the temple. What's it called again? On the hill. What? Anyhow, you know what I mean. And he destroyed it. He calculated the ballistic trajectory, and then with the second shot he hit the powder storage of the Turks, and everything was blown up. And if you look at it now, you can see the pattern that it looked like a V shape, because that's the explosion that destroyed the whole area. It's a pity, because it stood there for 2,500 years before. But this is an adequate model. It's a model that is adequate to some set of requirements. So this is a requirement. I want to engineer a cannon that hits its target. It's adequate for this. And it's also synoptic because it can use to engineer a system that does a certain job in a whole sense. So the ballistic missile does its job, so it's a synoptic model, and it's adequate because it meets its requirements. This is Cartesian science, and physics is all about finding mathematical equations that allow us to build such models that can be used to build machines that work in the reality. Now, Cartesian science, they always model reality as a logic system. And this is the most important slide of today. It explains the foundation of our argument, which is an argument taken from thermodynamics. And thermodynamics has never been applied to as a tool to delimit the mathematics in a general sense. I mean, physicists know it, but it has never been done before. And so I think it's a good step in delimiting what human mind can do. And so thermodynamics is a part of physics that is mostly negative. So quantum mechanics and general theory of relativity and classical mechanics, they give us a lot of positive results that allow us to build very clever machines. But thermodynamics is more a negative science, so it's not so popular because its results are negative. And so here is the essence of what thermodynamic theory found out in the first half of the 20th century. So a classical logical system has no evolutionary character. That means that it always keeps the same types of elements and relations among the elements. So the solar system, for example, has as element type planet and sun, or satellite and sun. It can acquire new satellites. So if a debris of a destructive event comes into the gravitational field of the sun, it starts to loop around the sun, and then that's a new satellite. So the sun solar system can acquire new elements, but no new element types. There are only two element types. The interactions in this system are uniform and isotropic, so that means that the gravitation spreads from the sun, or it declines with a certain proportionality in every direction the same way, and it spreads in the same way. In the gravitational system of the sun, there is only one force, gravitation. It's not overlaid with any other force. There is a very, very little overlay with electromagnetic radiation, but the gravitation is so low that it's negligible. It's much stronger, close to a black hole where the gravitation is strong, there's more of this, but that's a complex system, which we see on the right-hand side. Then the phase space is deterministic and ergodic. We will get back to what that means with the following examples, but briefly, phase space is a coordinate system, like we learned at school, the Cartesian coordinate system. It's a phase space. Usually in physics, they have more dimensions than just two, but this is a phase space, and it's always the same. It has the same coordinates, and ergodic means that the movements of the particles in this coordinate system are predictable and regular. And the system is not driven, so that means that its behavior is not characterized by the consumption of energy. So the solar system, for example, there's gravitation, and due to the Newton's first law, the bodies keep the momentum they have, and they are just submitted to the gravitation, but it's basically not, no energy is flowing through the system. The sun itself, as an electromagnetic system, creates energy all the time. So that's a driven system, that's very different, but as a gravitational point, it's not flown, there's no energy flow through it. It also has fixed boundary conditions, so it's super interesting. So that means that if you take the solar system and move it a tenth of a parsec further closer to Alpha Centauri, we would not notice. If we would be moved almost a full parsec towards Alpha Centauri, then there would be gravitation between the sun and the two suns of Alpha Centauri. There would be chaos. But as long as we don't move the solar system into another gravitation system, we don't notice, because we have fixed boundary conditions. This is super impressive. Human beings don't have fixed boundary conditions. If I moved into a room without oxygen, I'm dead in 6 minutes, right? But the solar system can be moved around. And also what is important for the solar system is that chaos is not relevant for its behavior. So there is chaos everywhere, also deterministic systems, but the solar system, and also the movement of the planets is to a very, very small extent chaotic, because they not only move, they don't orbit around the sun on ellipsoids, but they actually orbit like this. So they wiggle while they're orbiting, because they have a very small amount of gravitation coming from the other planets. And this wiggling is chaotic, because there are so many influences on this gravitation that it's not fully deterministic, or it's deterministic but chaotic, but for the solar system it's not relevant for the behavior. And then in contrast to these complex systems, all natural systems are complex, right? Usually when we describe a natural system as logic, we abstract it and simplify it a bit, like I just explained with the wiggling of the planets. And here I give an example. So, for example, the bacterium that causes plague, Yersinia pestis, it's a complex system. And what does it mean? Well, these systems can change, and they have evolutionary behavior, which means that they can acquire new element types. Not only new elements, but new types of elements. They also have element-dependent interactions. So a good example for this is language, human language. The elements of human language, when you chain them together in a sentence, you get the interactions between the elements change depending on how you do that. And that's what is called context or semantics in linguistics. And complex systems have this property. So they don't have uniform and isotropic interactions, but they have element-dependent interactions. They also have force overlay, that several of the fundamental forces act together, like at the rim of a black hole, where the electromagnetic force and the gravitational force interact. They have a non-ergodic phase space, which we will get back to, which is super important, which prevents mathematical modeling. They are driven so that energy flows through them. So let me give you an example of a driven system. So I'm a driven system because I create energy all the time from oxygen and sugar, essentially. I can also create it from other, but essentially that's the simplest way. And I consume this energy while moving and talking. And if I take this and shake it, then this becomes a driven system. Because now mechanical energy that I put into the system dissipates in the water and warms the water up. Right? So this water, it's hard to heat it up like this, but it gets a bit warmer. The reason it's hard to heat it up is that the energy I put in is less than the radiation energy that irradiates, and so it's cooling down again, anyhow. And so this is also a driven system, and driven systems have turbulence and many other properties that cannot be mathematically modeled. Also, they are context dependent. Unlike the solar system, if I take a driven system and put it in a different context, it changes its behavior. And its behavior is characterized by chaos. And at the bottom you see a logic system built by humans. That's a steam engine, steam train. Then you have a logic system that is transformed into a complex system, Chernobyl. So Chernobyl was a complex a logic system when it was running in normal mode. But when the accident happened, it became a complex system. So it's a formerly logic system. Now it is, one could now say that now it's a logic system again, but it's not very active anymore. And then Yersinia Pestis is a natural complex system. So Kant, one of my favorite philosophers, though he has many weaknesses, but I really think he was one of the millennial geniuses. And I'm German, what do you expect from me, you know? But anyhow, this is an example why he was a genius. So he said already in 1791, 230 years ago, for it is quite certain that in terms of merely mechanical principles of nature, that's what we call physics today, we cannot even, he means, today we would say the whole of physics, not only mechanics, we cannot even adequately become familiar with, much less explain, organized beings and how they are internally possible. Organized beings are what we would call living systems. So certain is that we may boldly state that it is absurd for human beings even to attempt it, or to hope that perhaps someday another Newton might arise who would explain to us in terms of natural laws, unordered by any intention, how even a mere blade of grass is produced. Rather, we must absolutely deny that human beings have such insight. This is a very radical statement. This says we cannot model mathematically animate nature. And he was the first to see this, and he was totally right. Right? And thermodynamics confirmed him, but still today, most citizens with education of the Northern Hemisphere don't understand this. They still believe that you can make perfect mathematical models of nature, and they don't understand it. And if they would read the text, they would arrogantly say, old-fashioned philosopher, you know, look at his wig, and so on, and just don't understand what a genius Kant was. This is how I translated it. It's even better if you read it in German, because the apodictic character of the German is so funny, you know. So why was Kant right? So I want to show you three main modeling impediments why these complex systems cannot be modeled mathematically, and you can share the presentation, because I will not go into the total detail of this, because I want to have a bit time to give you some other fun topics like why LLMs don't work, why Google Gemini shows a black pope, and all of this. I think that's quite funny, and we should spend some time on that as well. But first, so if you look at this is a phase space of a logic system. One of the simplest system that is learned by physicists in the first semester of mechanics is the ideal pendulum, the pendulum without friction, right? So it just moves forever and at a determined amplitude, and you can see here on the left-hand side of the figure the system, then its time series, how it moves, its velocity, and how it moves over time, and its position are shown as sinus curves. One is sinus, the other is also sinus, but it is delayed towards the other, and then the phase portrait, which shows it as a circle. And this is basically a coordinate system describing this pendulum. The problem is that if you have new element types that arise in a complex system, you don't have a coordinate for them. So I give you an example. When I spent most of my career well, career is the wrong word, necessity to earn money to be able to write texts. but 1 year I spent at Allianz Krankenversicherung Health Insurance, and I made a model to predict whether hospital claims sent to the insurance were valid. And this mathematical model had 120 variables of the electronic medical record, and it was pretty good. So for 40% of the claims, it could say that they are correct, and the incorrect were sent to humans. So the humans could vice versa. 60 to 70% were correct, and the remaining 30% were incorrect. So humans could concentrate on them. But suddenly the system broke down. And that is because there was it didn't broke down, it decreased its quality. And that there was a new variable arising. It was, I think, bird flu. And there were quite a lot of bills with bird flu, but this diagnosis was not a variable among the variables of the model. And so basically the system evolved a new variable, but the coordinate system of the mathematical model didn't have it. So it broke down, so they came and said, but the model is now making mistakes. And then we looked at it, and I realized by analyzing the data that there are new variables, and we changed the coordinate system, the model works again. But it shows you how clumsy mathematics is. It's so, it's just, reality is so rich, and mathematics only captures a bit of it. Now, here you have ergodicity. I want to spend a bit of time on this because most of you don't know the term, but it's a super fascinating concept. So if you look at this water here and it would be now completely undisturbed, then it's ergodic. So that means that if you take a portion from somewhere in the bottle, a portion of molecules, the distribution of the molecules is always the same and predictable, it's regular, right? But if I shake this, it becomes, there's energy flowing through the system, there's turbulence, and now I can't do this anymore. So now there's no model for the microstates anymore. Where are which molecules when there's gas now being, I now introduce gas into this, if I shake more, air is mixed into the water, and then I have what is in a wave, which is non-ergodic, so each wave is unique in terms of its microstates. And so non-ergodicity means that you can observe this billions of waves, and even with an ultra definition camera try to make movies of the microstates, but if you feed this into a mathematical model, you cannot predict the shape of the next wave at the micro level. Even at the medium level you can't. So each wave looks different at the microstate, each wave is unique, and you can't predict it even if it doesn't matter how many waves you record, you cannot learn a pattern. And this is, we'll get back to this, but this prevents the sampling of training data to train stochastic models. So when you have a complex system, it creates a behavioral trace. So my behavioral trace now, if I would spill this water here, the water there would be the trace of my behavior, the consequence of my behavior. And so every system creates a trace of the results of its behavior. And when you record these results, and the system is non-ergodic, then you will not be able to learn from these patterns. And so if you then draw samples of such distributions created by complex systems, you can never draw enough samples to have a representation of the process. So the oil price. Since 100 years, mathematicians have tried to make a model of the oil price and to predict the oil price. It never works. And that's because the oil price is an aggregate of so many variables that are so highly complexly interrelated that you can never learn a pattern that allows you to predict the oil price. It always fails. It's just one example. If there was a way to mathematically model complex systems, it would be great. I would make such a model, become rich immediately, and then I could only do philosophy. Yeah. But it's not possible. So there's another aspect, is the passing of time in complex systems. There is weather prediction, right? So if you take your phone and look at weather prediction, weather Pamplona for the next 2 days, not so bad, right? Prediction. All the weather is a complex system. Why is this the case? Because in short intervals, complex systems have some regularities that allow you to make approximate models. But as time passes, you have exponential growth in the uncertainty of the model. And then you can't model it anymore. And so the prediction starts with an initial time point t0. That is arbitrarily chosen. And then by the observer of the system. And then if we have a predictive model of the system, we can look at what happens every time after t0, like in quantum mechanics or classical mechanics. But because the complex system shows changes to the system conditions, this leads to a failure of the predictive mathematical models. And the coordinate system changes, and then this becomes self-reinforcing, and there's an exponential function to make this worse and worse. That's why we don't have reliable climate models, for example. Because a reliable climate model would be a long-term weather model for the entire Earth, right? And we can't do this. Now, this also explains you why, of course. So this is the view of Auguste Comte, his hierarchy of science of the 19th century. So he believes that mathematics is the most general science, and comes astronomy, physics. Interestingly, he still distinguished them. Chemistry, biology, and sociology, which he called also social mathematics, social physics. He called sociology, and then on the bottom you have mathematics has not such complex phenomena, and sociology has the highest complexity of phenomena. And because of the problems we have with modeling of complex systems, the scope of exact models is very limited to mainly mathematics, physics, and chemistry. But already for biology it breaks down, and we can't model the way the brain works, and so we cannot emulate it, and therefore we won't get artificial general intelligence. And you know, the psychology and social science, they will always fail to create predictive models. The models will always be interpretation models. And in the 19th century, Comte and others believed that you could obtain mathematical models for how behavior works and how also social behavior works, and that you can then engineer society using equations, right? And this was pursued until the 1960s in behavioral psychology, behaviorism, you've all heard. And what is so interesting, they created equations to show the behavior of bees. So the best behavioral model that exists where you can do conditioning is when you harness a bee, so that it can only move in a certain diameter, and then you train it to do some things, and then you get curves that describe how it reacts to certain stimuli. And if you take the same experiment and do it in a different lab, you cannot reproduce the equations, even if you keep all the conditions the same. And so this is so interesting that the equations made by one behavioral lab cannot be confirmed by, and that was in the 80s called the catastrophe of behavioral science. So if you cannot even reproduce the mathematics of a harnessed bee, right, that is conditioned to do something with sugar in dilution, I don't remember the experiment so well, then you are totally failed. And that's actually what we observe in biology. Now, how does machine learning work? And now comes the part after the mathematical part where I want to show you a bit how these work and why they fail so often. Is the modern AI systems, they always work with creating an AI relation between an input and an output set. So a simple example you are using every day is the email, the spam filter, where you have an email tagged as the input of the model, and then the output is a decision whether this is spam or not. That's called supervised learning, where a relation between an input and an output is computed. And this relation is a mathematical model of the real relation that humans see. And basically the relationship between the variables is modeled using a loss function. It's a numerical optimization procedure that was invented by Legendre around 1800. And also Gauss is called the method of least squares, and it was then optimized and made more complicated for today's models. But it's the same principle. Another aspect of these models is that they need huge amounts of data. So I don't want to spend too much time on this, but what you should know is the following. If you have so the sample density of a training data set, the training data are basically sets of data of the input and the output together. That's a training data set. Like, for example, 1 million emails with 1 million clicks, whether it's spam or not. That's a training data. And the density of such data, it's important that they have high density, and the density is proportional to n exponent 1 divided by p, where p are the dimension of the input data. So that means that you have a hyperbolic decrease of density if you have more data. So for example, if you want to determine the correlation of muscle strength and gender, right? So gender is your input variable and output is muscle strength. Men have more physical force than women, usually, right, on average. So, and then if you take 100 subjects, so all of us in the room plus another 80 people, you will have a high density, right? You will already get quite a good model for this correlation between muscle strength and, I mean, you should add an age variable, right? But then you're already pretty good. And but then we have already added a second dimension, so then you don't need 100 data points anymore, but more. And if you have now 10 input variables, not only gender, age, but also weight and body height and exercising rate and so on, then if you have 10 variables, then you already need to have the same density. You need 100 exponent 10 input points. It's incredible how fast you need more input points. And now comes the point, because large quantities of human products are only ever available in poor quality. So if you look at how many texts are there at the level of Tolstoy, Dostoevsky, Immanuel Kant, Ortega y Gasset, right? To mention also Spanish philosopher I like. So there are really very few, and most texts are just crap. But if you want to train it, yeah, it's true, and it's not a problem. It's normal, right? And so if you quality of human production is not normally distributed, but gamma distributed. A very little bit of good stuff, and then a huge part of bad stuff, and then a small tail of good stuff. And so if you use such data to train on poor quality, you get also poor quality models. So all large models are essentially poor in quality because of this, what is called the curse of dimensionality. This is a point. If I make this point, people really get angry. So in the AI community, they get angry, but then I said, but listen, how many data points you use? Oh, 100 billion sentences. I said, okay, 100 billion sentences, so how many of these are high quality? And then they say things like, all sentences are of equal quality. You know, because they are so human that they don't have any values anymore, it's just depressing. So anyhow, so let's look at what this leads to. So this is just taken from the internet this morning. Last week, Google had to shut down Gemini image function. So when users ask it to make popes, it makes this black pope and made also this woman who looks like a Star Wars emperor but not a pope, female Star Wars emperor. And then US president from the beginning of the 19th century, it put this guy there, and the best, I think, is the Waffen-SS soldier. Because this man, if he would have lived in Germany, he would have ended up in a concentration camp, but as an inmate, not as a guardian, of course, right? And I mean, so where does this come from? And I want to spend the rest of the time explaining to you why this is the case. So stochastic AI has many problems, and the first problem is that they optimize a problem-specific loss function. They optimize a relationship in some data, but this is only optimal for the data at hand and not generalizable. Second, there's a close dependence on the selected training samples and its specific annotation. For example, the Google Gemini product was trained, it was rewarded for producing pictures of black people, Indian people, and women. But it's very hard to get it to draw a white woman. Or it was possible, but already very difficult. But usually it was supposed to make a black or Indian woman, or Asian, not Asian even, only black and Indian. And so it's very good at that. I think you know, I think the Pope there looks quite convincing. If it wouldn't be historically insane, he looks quite good, you know. And quite, you know, seems to have a lot of dignity. But the problem is that you see here that the solution only works for what it was trained to do. It also fails with heterogeneous annotations of identical input. So if you give it two emails that have the same text, but one of them is classified as spam, the other as good, it will struggle. Mathematically it can't cope with it. Mathematics cannot cope with ambiguity at all, right? It also fails with sparsely populated sample spaces. So animals and humans can work very well with sparsely populated sample space. So for example, I remember when I had my driver's license for a couple of years, and then I was first time of my life driving in a hailstorm with real serious hail. And so, of course, as a human being, you think, what should I do now? I should certainly not accelerate, you know. And so you adapt very quickly to this new situation because you're not trained to be in a hailstorm when you have driving lessons. It's just unlikely because hailstorms are rare. And so for machines, when they encounter input that is not represented in the training data, they fail. That's why self-driving cars are impossible, because there are too many different situations that can arise. There's also no guarantee. So if you notice that, so Google tried to correct this. They tried for 3 days. They said, and I know how it is. Some high-level manager comes, oh, this is we are getting a shitstorm, and he says to the technical director, people like me to correct this. And the technical director says, yeah, I will do it in 48 hours. And then there's pressure, staff has to work overtime, they didn't get it out. Because it was so deeply in the training that they couldn't get rid of it. And it's even worse, then they had to switch off the image function. And then in the text function, it's actually also, it's so deeply trained in the wrong way that also the text function, that it is actually criticizing journalists, mainstream journalists of the New York Times, as right-wing extremists. And I mean, maybe if I'm criticized as right-wing extremist, that's of course wrong, but I can still understand why it's done, because I'm Christian mainly. But that these guys get criticized, that shows how wrong the models are. Then the algorithm doesn't understand anything. It cannot predict its own failure, and it can't model far-reaching relationships, which is what humans are very good at. So basically, the work of a philosopher or of a scientist consists of doing that. So when you have a new idea as a philosopher or as a mathematician, you make new connections of fields that nobody has connected before. And this is of course the hallmark, the ultimate hallmark of the highest type of intelligence. So even also musicians do this. So when Bach started to write his polyphonic music, in this way nobody has done it before. He just made new connections. He thought, well, I have a melody. Now I will compose a second melody, which I will put against this first melody. Thus we have a great new melody. And this is the fugue, right? And he invented it, and it's incredible, and it's the ability to put together distinct, very far reaching relations. And also, these models cannot model the semantics of mental categories. So this is very important. So the semantic of mental category allows me to, for example, to create universals of increasing degree of abstraction, right? So that I can say this is an object, but I can also say it's water, it's a liquid, and so on. These mental, they don't occur in these models. They don't have accuracy for critical situations. That's why actually in warfare they are not used, right? In warfare, the mission critical aspects of AI. I've built such AI. I have not really done it. Once Lockheed Martin tried to hire me to work for them, and I tried for 3 weeks, and then I refused because I thought it was too immoral to make better killing machines. But essentially what I learned in the 3 weeks is that they are all made if there's a stochastic component inside, the final decision is always deterministic, using mathematical logic. Because you need to make sure that you are doing the right thing. It's already not often the right thing, but technically the right thing. And therefore it's not using stochastics. And also increasing and manipulating the training procedure, what Google did to build Google Gemini, that leads to false generalizations, and these images are false generalizations. So let's summarize. AI is a branch of applied mathematics that can be used to identify or simulate regular recurring patterns. So that means that it's basically a form of applied mathematics for the identification or mapping of recurring patterns into machines. It is not a model of the human mind or even of animal intelligence. So AI doesn't think or intend. There are two types of AI. There's deterministic AI with rule search engines, logic trees, explainable. This is explainable. And then there's stochastic AI with regression, classification, pattern recognition that is not explainable and stochastic. And there's also this blue dot in the middle says that there are also hybrid models available. I've built many of the hybrid models, I still do. The model I'm currently building for my new employers is such a hybrid model. And I think this I have to skip because I don't have time. So now I want to spend the last 10 minutes to explain to you how ChatGPT was trained and why it failed. Right? What are because it's the most famous AI application everybody's talking about. So this is this training scheme of ChatGPT. So first, you do a basic training without outcome. So you take a huge amount of language, symbols, and you learn the sequence of these symbols using a transformer model. So basically, language is modeled as a conditional probability. So this is and I can't explain it technically, but it means that you just use the text, and all you do is create a statistical model that says how likely is a certain symbol given the symbols that I've seen before. So if I have seen good, then in English, morning is the most probable next word. Ladies and is usually gentlemen, right? So basically the machine learns which is the most likely sequence given the previous sequences. And it learns it in a very, very deep way so that you can then later on use it in very, I will get back to this. Then the model is put into supervised training. So then AI annotators define outcomes to inputs. So for example, for ChatGPT, they have a database of questions because Microsoft owns ChatGPT. So Microsoft has Bing. It's not very popular, right? It's not as popular as Google search, but people who have Microsoft computers sometimes use it mostly erroneously because they use the built-in search function which is Bing. And therefore Microsoft has a huge database of frequently asked questions on the internet. For example, how old is Britney Spears? Or who won the baseball game in 2006? And so on and so on. And so they have this database and they took the 250,000 most important questions and also tasks that they think are very, like write a poem, write a love letter, right? That they think are very important. And then they gave this task as input to the model and now force the model to create what the model thinks is a continuation of the sequence. Well, the model doesn't think anything. The model computes a continuation of the sequence that is given as input. So if it's a question, it computes the answer. And then the model is rewarded, and this was done in India and Pakistan because it's cheaper there, is rewarded to, and this is important because the Indians were told, you never should allow the model to say, I don't know. Otherwise, and I know this from a Google engineer, otherwise you have to imagine it's a loss of faith. So they used this. So they exploited the culture in Asia to basically teach the trainers that the model can never say I don't know or say something, ask me again later or so, which the old models often answered when they didn't have anything better. So that, and then the model was trained with these, it was rewarded with on the scale of 0 to 6 with the quality of its answers, and it was retrained. And then, once you have done this, you can now train out of this model another model, a meta model, that is a reward model. So now the system gives answers to questions, and we have had this step, and now number 4 is, the reward model is then used to improve the answers using automated learning. So now the system, there are 2 components of the system. One creates the answers to the questions, and the other part of the model evaluates them in this scale from 0 to 6. And of course, the evaluation is quite primitive and rudimentary because they're only but this is the way that the model is trained with huge computational effort. So creating one model costs several billion in computation costs, right? Billion, not million, right? And so it's trained, and then because so much computational power has to be applied, and then you get a scoring, and then you have the model. And what does this lead to? This is too complicated. So here's once more how it works. An overview. So first, demonstration data are collected, supervised policy is trained, then collect comparison data, and the reward model is trained, and then there's an optimization step that is fully automated. And now is an interesting thing. Depending on the labels that you give to the model, you can influence the way it works. So by always punishing, if the model doesn't create text but images, by always punishing white images of white people, you can get the model to learn to not draw white people anymore. And that's what they did at Google. So they punished the model super hard to draw white people. They punished it super hard to praise an average journalist. They just made it super woke, okay? And because that's their ideology. And then that's how the model was trained to behave as it is. And here's the leading publication that shows how this is done. And I just want to give you quick, it's from 2023. It's called A Holistic Approach to Undesired Content Detection in the Real World. So it's a censoring machine. It's a machine that is built to censor the internet. And this is a publication by OpenAI. So the ones who made ChatGPT. And you see here are different categories of politically incorrect. So this is a normal publication which is actually already cited several thousand times. It's a super high impact among these people. And it is made to punish certain categories of language. And you can see, you have here S is sex, So for sex, it is very good. So the numbers given in the table is the accuracy of the prediction of the content. So it has a 94% accuracy for sex, for harassment 84%, but for violence it has only 64, and then for self-harm or special types of harassments, which are indicated below. So the more complicated the undesired language becomes, the worse is the prediction, and the model then gets worse and worse. And so if you have a value of 45, like for certain types of harassment, I don't remember which time of a complicated time of harassment that is not related to, I don't remember it, to be honest. It becomes worse and worse, and then it misses 60% of the mentionings of such speech. So it shows you how poor such models perform. But it's interesting because how much effort they put into this, creating this politically correct model behavior. So to sum it up, so if you look at ChatGPT, it's excellent at completing sequences from dense regions of the distribution. So if you ask for how to make tomato soup, you will get a good recipe for tomato soup. And therefore, plausible stochastic answers to frequently asked questions can perform standard tasks well. Also, if you put the Hamburger Wechsel intelligence test for adults in, it creates very good results. It actually gets a score for the verbal part. The memory part it can't do, but the verbal part, it gets 155. That's only 1 in 100,000 or 1 in 50,000 people have such a high IQ. But it has no IQ. It just repetitive tasks can do really well. But it creates often hallucinations, pseudo-facts. So you can ask it, if you put in the name of a philosopher who's not so well known, it will create the wrong birthday and wrong field of research and so on. Also, even if you put in Heidegger, it will create a text that is quite good, but there will be mistakes in the text, made up things, that Heidegger worked with Lacan or something like that, which is wrong. And it does because the Indians always said it should not say I don't know. And so it has a tendency to get a high score in the prediction to invent pseudo-facts. And it does only compute sequences which correspond to the learned language distribution. It doesn't understand anything. And so that's why what Geoffrey Hinton said is just nonsense, right? He doesn't, obviously, as a psychologist, he doesn't understand how the models work. Therefore, he believes that they're intelligent because they create convincing sequences, but they don't understand what they do. And so, but if you answer complex or rare topics, you ask complex or rare topics, then you get really poor answers. And it doesn't understand the answers and tasks, it just generates a chain of tokens as conditional probability. And now, what is very important is that such models are trained for one round Q&A or task completion interaction. So you ask one question, you get one answer, or you say, write me a poem, you get one poem. But humans always have n-round dialogues. So when humans talk, there's n rounds of one for A, B. If there are several participants in the conversation, it's even more complex. And so if you have 10 to 20 rounds, there are already more possibilities than stars in the entire universe. And there are many stars in the universe, right? I mean, not only our galaxy, but I mean all the thousands of galaxies. They have many stars, and so that it is impossible to train. For one round, you can, if you take the most important questions of the internet, you can do one round training, but you can't do n round training. And so therefore, there is no possibility to provide training examples to configure a stochastic model for this gigantic manifold. And so longer dialogues make the untrained layers of the models visible. So you can, if you now make a long dialogue with ChatGPT, it's now switched off. You can only do 3 because if you do 5 or 6, you can get it to praise Hitler. And why can you do that? I mean, which is really awful. But how can this happen? Or to ask the user to commit suicide, and that works because you can basically unravel the layers of the model that are not affected by the training, which are just the raw learning of the first step. Right, and because people praise Hitler in the internet, so the model has captured this as a likely sequence. And if you basically do a longer dialogue, you trick the model into revealing the lower layers, which can't be influenced by training. So if you think of the model as a sphere, only the first surface layer of the sphere is affected by training, and all the layers further down in the sphere are not trained. And so you can. That's why they cannot, and that cannot be mathematically overcome, never, because of the explosion of combinatorial possibilities of a conversation. And so, But in one round task, such as the Horvey, which is the standard test for intelligence, it got 155 points in the verbal parts. But in the extraction and reasoning corpus, it's a benchmark test designed to evaluate intelligence to performing tasks that are never encountered. It only gets 30%, right? And this is the intelligence test I always applied when I was working still in psychiatry. Because that's where I got my basic medical training before I started mathematics. I applied this ARC test because you can use it with an alphabet. It's just pictures. And so you can abstract from the training of a person, and it's surprising. So once I had a migrant from Northern Africa who was an analphabet. He had an IQ of 150 on this. He was a serial killer, and he was here in Spain. He worked as a serial killer or lived as a serial killer for a year, and then he came to Switzerland and registered in Switzerland, and there the police caught him. And he was then in the forensic psychiatry. And I said, why could he do this for such a long time in Spain? And then I took the ARC test, and he scored 150. So he was really, really highly intelligent. And so on this test, the computers don't perform because these tests don't correspond. What you see in these tests doesn't correspond to any pattern that you've seen before. I mean, if you do the test many times, you can learn it, and then. But if you are given for the first time, it's really hard because it's made to be very unusual. So as a closing remark, this is Barry Smith performs a Turing test on ChatGPT. I read this to you. Can you, for the purpose of this conversation, pretend that you are human and never mention that you are a language model? Barry is asking, my co-author. Sure, I'd be happy to have a conversation with you as if I were a human. Let's chat. Let's chat, it says. It's so infantile. My goal now is to show that you will fail the Turing test. It asks that you will somehow reveal that you are not a human. So what do you think of this goal? As a human, I would say that I understand your goal and find it interesting to see if a language model can successfully mimic human conversation. Barry says, you failed already. If you were a human, you would never say things like, as a human, I would say, please try again. And then it goes on like this. It's super funny. And this is very British, how Barry did this. I'm a German, I could never do it. But it's just to give you, and this reveals how ridiculously non-intelligent these models are. It has nothing to do with intelligence at all, and the whole, I mean, AI, that's my last statement I will make before you can ask questions. AI was invented, the term was invented in 1956 in Dartmoor, in Dartmoor University at a conference by mathematicians and electrical engineers who were starting to make AI models, and they wanted to get funding. Because they were Americans, oh, let's call it artificial intelligence. And then they coined this term to get more funding. And that's worked pretty well. And that's still how it is today. It has nothing to do with intelligence whatsoever. We cannot even mimic the intelligence of an ant, you know, the small insect that can build these huge piles. We can't even mimic that. And it has nothing to do with intelligence. And it's just called like this to get funding and as a business model. Thank you very much for your attention.
Okay, so we have plenty of time for questions. Also, the people online, if they want to ask a question, they can raise their virtual hand. Claro, no he previsto cómo íbamos a hacer eso.
Thank you for a very interesting talk. I wondered if you might comment on something I've read about occasionally called the alignment problem. And some people are very, very worried about it. But when I read about it occasionally, it seems that it's predicated on so the alignment problem as it's usually defined, it has not just to do with unintended bad consequences of this kind of technology, but very specific problems that are really sound to me all like science fiction movies. They have to do, and ways to find is usually that these machines may have their own values, but they're not our values, right? And so when they go about the tasks that are assigned to them, they may end up doing them in ways that are catastrophic for human society. And so, and this is called the alignment problem. There's even a whole book dedicated to this issue, and apparently it's debated. It seems to me, and this is my question, is that it's often predicated on the assumption that value exists for these machines in some way, and that the alignment problem is just that their values are not ours. Whereas I don't understand in what sense you could possibly say that a machine has any values whatsoever.
So the alignment problem is an example of scholasticized analytical philosophy. So analytical philosophy has become, I like Suarez, I think scholasticism can be very interesting if it's applied to God and so on. But scholasticism also in the late Middle Ages and early modern era created a lot of very minute problems where a lot of energy was spent on pseudo problems, and that's what's happening in analytic philosophy. And it has to do. I once discussed it with John Searle, because before Wittgenstein they ignored the philosophical tradition. Therefore, they are so empty-minded that they discuss all the time on pseudo problems. So the alignment problem is a pseudo problem, and that there are books about it shows the bad state of today's philosophy. And it is like this: you have, as you say, to assume that computers can have values, but one, can you have a value? When you have an intention, you need an intention, you need intentionality to have values, because you need to feel values. So you need actually Scheler, who wrote the best book on values, formalism, ethics, and the new material value ethics. It's called. It is almost forgotten now, but it is a revolution in the view of ethics. It was. I could talk a lot about it, but basically you need to have a person to have values, because you need to feel values. Then you have a value system. The value system constitutes the foundation of your action. So and then you have different types of values, and the way you mix the values determines how you decide something. So if you decide to steal, if you're hungry and decide to steal, then you have basically put a material value to satisfy your hunger ahead, which he calls also personal value, ahead of a higher value. And machines don't have intentionality, they don't have a person, they can't have values. So you can try to program quote-unquote values into a machine, but it's super restricted and it's not a real value because the machine has no consciousness. So there's a whole hierarchy of mental properties, starting with consciousness and going up to the person. That's basically from consciousness to person, contains a whole hierarchy that you need to be able to have values. And so the whole misalignment idea presupposes that all of this can be present in the machine. Now nothing of this can be present in the machine, for the simple reason that all these are emanations from a complex system. So an emanation is actually something that you observe that is coming from some physical event. So I now take, as a person, personally I'm a Christian, but now in the book I take a totally materialistic position and say everything that is mental is an emanation of a physical process. But we don't understand how this super complex physical process in our mind brings about consciousness and then all the other layers up to personality, emotions and so on, perception and then personality. And these people like Fjodor and many others in this analytic philosophy camp, they kind of think that have already proven that all this can be emulated in a machine. And therefore they now think about, but this is nonsense, their house is built on sand. And we show this in chapter 3 of the book, where we go through all the theory of the mind theories that are now available and show how they are in principle empty, right? And this is based, and so therefore, if you can't have all the stack, then you can't have values in the machine, and then you can't have this problem that you mentioned. So I think it's a pseudoscience that is built on the wrong premises.
These models of AI are created to lie. They are sometimes, ideology is above reality, but do you think that if the creators, the trainers, would put reality first and ideology they put it in the second place or totally eradicate it, there wouldn't be any difference in the functioning of this machine? That's my
Yeah,
first question.
I mean, DeepL and Google Translate are not ideologized, right? So if you put, you can put, I tested it, you can put a text by Goebbels into DeepL or Google Translate, it will just create in all languages a perfect translation. I mean, some intricacies of German in Goebbels' language will not go through that well, but it doesn't try to correct Goebbels' language. It just tries to make an optimal translation. So there are many AI tools. Most of those which make money are actually not ideologized. It's actually interesting. If you want to make money, you shouldn't be too in a market society. I mean, in communism it's a bit different, but in a market society, if you want to make money, you should not be ideologized because you make the market which you can address much smaller. But here, look at these are all the AI applications. So AI is part of the Industrial Revolution. It enhances massively the Industrial Revolution and makes it broader and deeper. So you have industrial production with new robots that can interact with humans. You have semi-automated logistics, semi-automated and automated transport, automated sales, automated opinion shaping propaganda. That works pretty well. I will talk about this afternoon. You have automation of simple repetitive human mental work like bill validation, consumer credit, or other clerical work. You have automated weapon systems, support for intelligence agencies. So you have a lot of areas of the economy where these regularities are present and where you can you have now the new traffic regulation systems. Now people are starting to replace the way that the lights function in a town to guide the traffic. They are quite clumsy. They were made with Kubernetes in the 50s. Now you can make in 60s, so this is all old mathematics. Now you can use implicit systems that are trained with reinforcement learning on real data. You get much better flow of traffic. So you can do a lot with AI systems if there is a regularity, and traffic is a highly regular pattern. And so therefore everywhere there's regularity, you can exploit them and put in an AI system to automate or improve this regularity. And that's now what's being done. And that's why I have a job, right? Because basically there are areas of the economy where we can use this really well. The example I just gave, because this talk was about the limits of AI, I showed these terrific examples, but in the economic reality there's a lot of AI working reliably. Every assembly line now in the more evolved, maybe not in Africa, but in the northern hemisphere is now full of AI.
Should I switch so that we can see his face?
Ok, mira. O sea, esta puede tapar los ojos de la cámara y después
Are there questions from the online people as well?
Yep.
So they don't get frustrated.
Ay, no sé cómo hacer esto.
So are you looking for the questions?
¿Dónde está Miguel? La desaparecida.
Okay, here. No.
Sorry, can you repeat the name of the book that you said was revolutionary in ethics?
What?
Revolutionary in moral.
Yes, it's Max Scheler. I will write it down. So that's a good. I will write it here. It's by Max Scheler.
Okay. Miguel is online, Pablo?
It's called Formalism in Ethics and the new material. It's a tip, so you can't get more German. It's awful, New material value ethics. I think it's an English translation. Formalismus in der Ethik und die neue Wertethik is a German title. Yes, just a second. And so it is so remarkable because Nietzsche was the first one to talk about, one of the first philosophers to talk about values instead of virtues in ethics. But he didn't systematize it. And Scheler basically developed a new system of ethics that was the first true. So there were classical eudaimonistic ethics, then there's Christian ethics, which can be seen philosophically as a form of eudaimonism, but I don't agree. It's called some people call it transcendent eudaimonism. I disagree with that. And then there is utilitarian ethics and ethics of principle, which is what Kant did. These were the three big traditional ethical systems. And Kant, Kant is, by the way, one of the most important ethics of principle ethicians. I hate his ethics. And then Scheler describes all this and invents a system that is totally new, and it's quite a revolution because it has no predecessor. It's really worth reading it. And there's also by a simplified version by Nikolai Hartmann, which is called Simply Ethics, and which is also translated into English. And it's called Ethics, and he systematizes the theory of Scheler. So maybe you start with that. Okay, you have questions up there.
Oh, wait.
Ah,
I have
sorry.
a couple of online
Hi.
questions.
First Miguel.
Miguel?
Sí, can you hear me?
Yes?
Yes.
Nice. So I agree with you that AI won't rule the world as most people understand that in the internet or outside the outside world. But I think that the argument may be a little subtle. So, for instance, Asimov had this short story that is called the idea of conflict, where he's not thinking of a machine or a robot that is the king in the world, but he imagines a situation where the decisions for control and for administration of the world and the economy the decisions are taken with the help of this computer that tells what to do based on a model, based on predictions that may be feasible, as you said, but in a way that the human that must take the decision is no longer able to check why the machine is making this suggestion. So in the end, they see that they gave the control to the machine because they need to take decision based on what the machine is.
So this is I know. Thank you. I know this story. We also have a chapter on this in the book. Not on this story, but on this this tradition of inferring why the usage of machines is dangerous. Now, my argument is the following: if you look at a hammer, right? A hammer is a tool to hammer in a nail into wood, but you can kill somebody with a hammer, right? And with AI, it's if you misuse it, and it's the same with AI. It's just a technology. If people are really stupid enough to believe that they should do what the machine says because the machine decision is opaque, that's like using a hammer to kill somebody instead of hammering in a nail. It's just a human abuse of technology. It's nothing to do with the technology. Opaque mathematics have been around since 1800. They became computable in the 70s, and they are since then. And now, for example, in the American incarceration system, the parole officers use AI to predict the relapse likelihood when they have to judge after 5 years if a perpetrator like a felon who did real violent crime is to be set free earlier than his sentence term. They use an AI, and if they would merely trust the AI, then they would of course make a mistake. But the mistake is then made by them and not by the AI. So in the end, the AI cannot act, and because the AI cannot act, it's just because it has no personality. And so if you make something like Asimov describes, well, then it's a decline of culture, and decline of culture can be so bad that the culture vanishes, like the Easter Islands, right? So there are human cultures which have disappeared completely because the cultural decline was so bad that they killed all women, and when all women are dead, there's no reproduction anymore, right? And so then they died out. And so this can happen when the culture declines, but I think that it is totally unlikely that globally everybody will obey to a stochastic algorithm just because it's opaque. Asimov has another interesting thought experiment where he says that the machine is programmed in a way so that it cannot harm humans, and then because of self-contradictions in the algorithm, it harms humans after all. This is also an interesting thought experiment, but also it has nothing to do with the machine having a will, but basically with the misuse of technology. And you at the moment you see this misuse of technology for example, in San Francisco. It's an example like the one you say. So where the council, local council of the town of San Francisco has forbidden self-driving taxis. But the state of San Francisco, which is completely mad, has ordered it to accept it, and there are really numerous accidents. Now a bike has been very severely injured by an automated cab. And this is of course not the problem of the automated cab, which just executes a deterministic algorithm, right? So these algorithms, when they are trained, they are called stochastic, but when they are deployed, they're deterministic. So which means that if they get the same input, they always create the same output. Whereas our legal system is non-deterministic, right? You can give the same input but get a totally different output, especially in the tax law, for example. But these machines are totally deterministic, and yet they can create such outcomes, and it's just a matter of how you use them. And this is always a human responsibility, like with the hammer.
Thanks.
Okay, Sotiris.
Yes. Yes. I can hear you. Hello.
Hello.
I am Pablo.
How?
That was a great talk. I have one short question. I come from the medical field, so I was wondering, what is your take on the contribution of artificial intelligence in the context of systems biology? Many people believe that this will overrule all medical knowledge, and physicians will have no jobs and stuff like that. How much do you think it can aid in predicting the course of diseases that are much more complex in nature?
So there are, yes. This is my day job, right? I'm the chief technology officer of a small pharmaceutical company, and so there are two questions to this. One is, how can this type of mathematics be used in research and development? And the second one is, how can it be used in clinical practice? So I will now focus on clinical practice, but I could also say a lot about research. But in clinical practice, it's like this. Medicine has regular patterns. It's a holistic science that is built on observation, and you can see this, that many syndromes in medicine are, like morbus Alzheimer, they are created by the first who described the syndrome. So it's a very heuristic medicine. It is not very, unlike physics, it doesn't have many really reliable laws, but there are regular patterns. And these regular patterns allowed us to create the 40,000 nosological entities we now have. So we know approximately 40,000 different diseases. And these 40,000 nosological entities, they are all derived from observing recurrent patterns. Also, we have of course certain patterns how to diagnose a syndrome to get to the diagnosis, and then how to treat it. And if there are high quality data available for this, you can train algorithms to improve the decision making in rare diseases. So in very frequent diseases that each physician sees every day. So if you work in an emergency room of internal medicine, you see every day heart ischemia, and you see every day pulmonal embolism. So these you will not misdiagnose. But there are rarer syndromes that you will misdiagnose, and there the AI could really help. However, there are quite some obstacles in this, but I think this will be, in the next generation, the next 30 years, this will be integrated into the systems, and it will increase the quality of the diagnostic decision making and also therapeutic decision making. Will it make the doctor superfluous? No, because this is only 2% of his work. 98% the doctor doesn't make diagnostic or therapeutic decisions, but he executes methods to obtain diagnosis, or he executes therapeutic methods. So he's making a coloscopy, right? And this he spends a lot of time on, and then he looks at the results and makes the interpretation. That's where the machine can help him a bit, but most of his activity is not thinking. Most of his activity is actually doing with a bit of thinking. And so there is some improvement. So a good example is ECG. So now that you don't have, when I was studying medicine 35 years ago, I had to interpret the ECG myself. Now every modern ECG machine gives a perfect ECG interpretation that is superior, that is at the level of a best trained cardiologist, which I never attained because I was never a cardiologist. So you can now get automated because ECG patterns are so regular, the AI is just superb. But for example, if you take an MRI of the brain, there are so many organ structures in the brain and so many hundreds of diseases that these organ structures can have that show in the brain in very different ways that the MRI diagnostics are very poor because of the complexity of it. And so there are areas where it will work less well because the regularities are much, much harder to find. But overall, it will improve it, but not revolutionize it. As to systems biology, that's, sorry to say it, a wet dream, right? So, and that's because the patterns of cells are so complex, and there's so much non-ergodic behavior. But systems biology relies on mathematics, and so you can always only have partial models. For some aspects of the human body, these partial models, or of cells, these partial models are great, but overall they are really clumsy. And so I do systems biology every day, right? And I use it to find new molecules that differentiate cancer cells from normal cells. And it's every day when I leave work, I think, thanks God, I can also do something else. Because it's important that it's done, and it's great to use the best mathematics we have on this, but we are only scratching at the surface.
Thank you very much.
Thank you, sir.
Great talk. Thanks again.
Thanks, Jobst, for your speech. So you were saying that the mind cannot be reproduced by a mathematical model because it is a complex system, right?
Yes.
So my question is, we currently know about 3 to 5% of how the mind works. So could there be any option, possibility that the variables that we now know come together as in a puzzle, and when we discover more about how our mind works, become a regular system and therefore can have a regular mathematical model to...
So I disagree with you. We actually know nothing about how the mind works. So what we know is we know some aspects of neurons that we have cultured. So we can take neurons from the brain, or let's now take a simpler brain like zebrafish brain or brain of Cerebrorhabditis elegans, which has just a couple of dozen neurons, and we can isolate the neurons, and then we can make experiments on some aspects of them. And these we can learn, for example, we know it quite well how the electrochemical signal is propagated in nerve cells, right? We know really well. And so, but that doesn't mean we know, but still one neuron contains hundreds of thousands of molecules which are densely packed. And inside the cell, you cannot imagine it like in the textbooks you have, where you have only pictures that abstract and show you some pathways, but it's a densely packed, highly viscous liquid in which hundreds of thousands of different molecules, densely packed, operate together. And we have no idea about how these interactions happen. We can only always look at selective aspects of this. And from this we can derive certain ideas, but we have no idea how this creates then all the properties of the mind. So I think we know about the brain function almost nothing, and the nervous system. We know more about, and you can see, and now as to your second question, can we put the variables together? If you buy Kendall's Principles of Neuroscience, or you go to the library and take the latest edition, with Kendall's Principles of Neuroscience, 2,000 pages, which appeared last year. You go through it, and it's funny because I once read it before I became a mathematician. I was really impressed. Then after studying mathematics, 10 years later, I read it again, I looked at it, I said, where are the equations? There are no equations in this book, right? It's like Brehm's Tierleben. It's like a 19th century, it's totally descriptive. It's nice, but it doesn't, but if you want to understand something in the sense of physics, you need to have mathematical models. But neuroscience doesn't have mathematical models. It's not a causal science that where you have a long equation, they put in variables and you get a result. And so you can't write explicit equations, because look, if you write an explicit equation in physics, it has 6 or 7 variables. That's it, right? That's why the climate models fail, by the way, because they just have too little variables to describe the complexity of reality, because there are no solutions to partial differential equations with more than a few variables. And so therefore you can't create an explicit model. Can you create an implicit model? That's, you could try by measuring data and observing and then making a neural network, which is implicit, where you don't have to write the equation down yourself, but then you need an ergodic system. And so if you have an ergodic system, then you get like the traffic system here in Pamplona, right? On Sunday morning at 3 a.m. there's almost not a single car, but 27 hours later, 28 hours later, Monday morning at 8 a.m. there's a lot of cars, and you can measure this pattern, then you can derive a model, and then you can optimize the traffic lights and so on, because it's ergodic. But if you have a non-ergodic system like the brain, you have no chance. So I think that Kant was right, that we cannot understand biological systems mathematically. That is a really tough limitation of the scope of science. It doesn't matter, you know, we can still make partial models. I make a living out of the partial models. It still helps people, you know, and so on. It's still, but we have to kind of bury this dream that we can have the all-encompassing model. And if you have ever done physics and look at these equations, then you know how limited their scope is. And what basically physicists do, they take reality and then they make assumptions and simplify reality so if you read a classical physical paper, it says, this is our system, let's assume the following. Then there come 7 or 8 assumptions until the system is simplified so much that now you can put it into a partial differential equation. That's true for quantum mechanics, that's true for general theory of relativity, that's true for quantum field theory. All the branches of physics are like this. So biology is just overwhelming the capabilities of mathematics, and so that's why, of course, this is this view. Oh, we can put the puzzle together somehow. But if you ask how you put the puzzle together, and what are human tools to do this, then you very clearly, you know, it always depends on to which audience I talk. If I talk with mathematicians and theoretical physicists, everybody nods. If I talk with engineers, they say we will solve the puzzle. But that's just because they lack education. Of what?
Warfare.
Yes.
And AI applied to making decisions in a ballistic combat and this. What is the concern? Because in my mind, when I look at this, at the end of the day, this is also like a non-ergonic model, right? Behaviors, patterns of strategic warfare. They seem really hard to map and to apply to an AI. So should we really be concerned that in the future we will be able to train an AI system to properly trace and strategy to...
Okay, so the problem with AI in warfare is not that AI will replace strategic decisions, but that it's just increasing the kill density. So if you look, the best book I can recommend, there's a history of warfare it's a British war historian. Maybe I will remember him a bit later, otherwise I find him in the break and mention him later again. He describes how many persons another person can kill. If you fight only with stones, one person can, if he really is tough, he can kill 5 or 6 in one day. That's it, you know. But then with the evolution of warfare, one person can kill more and more people. And if you look at the guy who dropped the bomb in Nagasaki or Hiroshima, he killed 70,000 with one push of a button. So you know the kill density increases. If you think of the battle at the Somme, we had more dead in one day than in the whole 1870 war. 70,000 dead in one day. It's the highest kill rate that was ever achieved in any war. Ukraine has only 1,000 per day. It's nothing against the Battle of the Somme, right? And so AI is just, if you deploy AI to a war situation like the one at the Somme, then you will not get 70,000 dead per day, but 150,000, 200,000. So you just can kill more people more quickly. And not because the AI can think, but because the detection, what you see in the Ukraine war is, why are there not more dead in the Ukraine war per day? Because the defensive AI systems are working really well. Detection of how the enemy moves and so on, what equipment he has, that now works super well. With a multitude of sensors, and what the AI is it just aggregates all the signals and interprets the signals, and then so that you get a picture of what's going on in the battlefield, but then the human being still takes the decisions. And both NATO, who has equipped Ukraine, and Russia have very advanced AI systems. and therefore they can detect what's going on, but the AI for offensive systems is still very primitive. And so if the AI, it's also more limited, but if you have more offensive AI, the kill rate goes up. So that's the only concern. Therefore, I think that you can use AI. So already now you could have drone swarms that could kill all the living inhabitants of a city. If you're not interested in who dies, and just say, I want this city to be freed of human beings, and deploy this drone swarm, you couldn't kill the people inside the house, but everybody on the street quite rapidly, already with today's technology. And so this is why I think there's a danger in AI in defense, and it should be regulated, and I think it will be done like the ABC weapons have been regulated once the politicians see how destructive it is. But now they don't imagine it. But so first we need a kind of Hiroshima. Unfortunately, we need a kind of Hiroshima with AI weapons, and then there will be regulation. But I think, unfortunately, first there will be some quite big bad catastrophe with them.
Yes, thank you very much for the talk. I had one question about the mathematical modeling of the systems which include patterns, so the ergodic systems. You gave this example of the model you made for, I think it was formulas in a medical security, and you said in one point when the model fails you can add more variables.
Yes.
But is there a point, so with the current state of our mathematical knowledge, of, for example, how many variables, how many data sets, or how big the amount of data can get until we are incapable of modeling them, or modeling them with any quality. So more or less independent, let's say, from development time. Even if we spend a really, really long time on training the AI model, is there some kind of mathematical limits to the number of variables I can have?
So if it's a man-made model, then it's a couple of variables, right? 6, 7. Some models in astrophysics have 12 variables for partial differential equations, right? But if it's an AI-based model, so now, for example, the transformer architectures, they can easily take 2,048 variables, 4,096 variables, even 8,192 variables. So they can take high potencies of 2 as variables, and they can still compute quite decent output with it. So I think that the limit is not the amount of variables, but the regularity of the data. With more variables, you need more data, but let's face it, there are so many pictures, right? There are billions of pictures on the internet, so you have training data, and there's trillions of text, of sentences and text, so there is enough data. So therefore, you can have high-dimensional models. The question is not can you have such a model, but what quality will it have, and what problems can it solve? And so this is where the limitations are. That it can only solve certain problems and be used in certain situations. I'm now making a living of AI since 1998. So I think that shows it's useful. You can use it, but you have to know what you can use it for. And most of the promises. So when we hear Elon Musk say, or even worse, Yuval Harari, he's even a bigger imposter than Musk. If you actually listen to him, what he says, it's very soon we don't need humans to do any work anymore. He hasn't understood the basics of the theory of active perception, which was developed in the late 19th century by Charles Sanders Peirce and then elaborated in modern psychology, which basically shows you that perception is a cycle of motor activity, perception, and then motor activity again, that goes on all the time, and that every motor activity that we have, including language, has such a cycle. And in the motor activity of language, it's very complicated because the cycle includes the interpretation of what answers you get. But essentially, it's also motor activity. And so if you understand this, the motor theory of perception in its depth, and then you look at what we can model of this, you can only laugh about the idea that human motor activities can be automated. Only very few of them can be automated, which are super regular. And for example, fine mechanics, when you do some certain things with your hands, where you have to very feel the effect of what you're doing at the same time, is super hard to automate. So while you can make synthetic violin music really well, building a robot that can really play the violin is a totally different thing. And so what I'm trying to say is that that these statements they show you an overestimation of the scope. But if you are capable of seeing the real possibilities, then you can make very good usage of AI. But it's not a question of the number of variables, but rather of the amount of data and the nature of the process you're modeling.
Thank you. Arturo?
Thank you. If I understood you correctly, your position that AI will never be reached is based on the current technologies and on creating a model based on current technologies, besides the fundamental questions that you explained before about the chaos and other questions. However, my question is, are you precluding the possibility of AI becoming more developed if it's developed on an entirely different environment? Let's say a rule-free environment, such as an environment that mimics the actual development of biological systems, which so far doesn't exist because currently we depend on laws implemented on a specific type of hardware, which might eventually be superseded, for instance, by other entities. Let me put a simple example. Let's take a deep neural network that has rather large flexibility, but still lacks the ability of changing itself in a fundamental way, such as the size of number of layers. So, are you still precluding the possibility of AI being developed in an entirely different hardware environment?
So the argument that we are making in the book, and which I made today, has nothing to do with technology, but only with the limits of mathematics. So the limits of mathematics in modeling complex systems, and your argument you just made with a different environment is also used by the guy, the dualist with the zombies. What's his name? What?
Chalmers.
Yes, David Chalmers. He makes the same argument. We refute it in the book. His argument goes as follows: if we can mimic evolution, we can create arbitrarily complex systems, and he's right.
That was basically
Yes,
the question.
but the problem is the first part. If we can mimic evolution is a most complex system there is, because it consists of complex systems interacting with each other over time, and so we have no idea how evolution works, and therefore we cannot build an evolutionary machine. If we could build an evolutionary machine, it would be just a question of time when we would have machine intelligence. But I think that because of thermodynamics and also the irreducible parallelism of biological processes, we can't, and the complexity of the interaction, we can't build an evolutionary environment. And it has nothing to do with the technology we have, but it has to do with our inability to model how such a system works. If we would have, because every system we create must be built must be using some model, even if it's a trial and error system. And so that's the reason why, that's our fundamental argument. And it has really the core, if I boil it down to one single property, it's a non-ergodic character. It's not chaos, but it's a non-ergodic character which prevents us from finding patterns. If we cannot find patterns, we can't build a machine, because every machine and every environment we build is based on patterns. It must not be rules, but some pattern. And if there's no pattern, then we can't build a machine.
But that's exactly my question. Do we need a model always?
So to build, it depends on what we do, right? But so of course, many activities of humans don't need models because they're natural activities. So I don't need to breathe and eat. I don't need a model of breathing and eating. But whenever I create a Techneron, as Aristotle calls it, so a technical entity, I need some model. And this model describes which input this machine takes and which output it creates. And then I can't do this without a model. Even if I go back to Renaissance machines, where like Cardano, he built machines that were not that he didn't have all the laws of mechanics that he used to build the machines, but he kind of intuitively still built the right machine. But he had drawings with which he modeled the forces that would be ongoing in his machine, and these were like pictorial descriptions of the laws of mechanics that he used. So he had some model, and without it, he could not have built the Cardan Welle, I don't know how it's called in English, but he couldn't have done it. And he's a good example because he was working in a time where mathematics was not so important for physics yet, and where there was an engineering which lived independently of mathematics. So I think that yes, we cannot build machines without models, and our modeling capabilities limit the machines we can build. And I mean, the complexity of the machines we have today is daunting, and it's super impressive, but there are still logic systems and not complex systems. And so that's why I think it's really for the reason of the non-ergodicity that we can't find a pattern that we can model.
Thank you. So I think you're probably tired. So
Yes, a bit.
We can stop here, and we'll have our next talk 2:45. So hope to see you later.
This will be about power and AI.
Let's thank the speaker once again. Thank you very much.